Okay, so here's where we were last time. We were talking about boundaries. I remember, we're doing a lot of setup right now, right? I'm making a bunch of arbitrary definitions and choices, conventions. So this is going somewhere. Right? Once we get all of these choices set up, then we're going to start writing down some equations that lead to other equations and natural thoughts. And lo and behold, we're going to start making theorems. Right? Okay, but we got to get the groundwork laid first. So reminder, the last thing we did last time, we were talking about, so we have an interval. And what does it mean to talk about the boundary of the interval? Okay, wait a minute. That's not really what we're talking about. We have an oriented interval, right? Everything is oriented now. Everything has an orientation. Even if it's not something we normally thought of as having an orientation. I mean, we're very comfortable with the idea of a surface having an orientation because that tells you which direction you mean is the positive direction of flux of a fluid through that surface. But what does it mean for an interval to be oriented? Well, it's a convention regarding sign, right, in an evaluation. So this interval is either positively oriented or negatively oriented. There's no geometric interpretation. It's just something that's a concept that we're tacking on to this otherwise familiar set. Okay. Right. So if we have a positively oriented interval, then what are the boundary points, but more relevant, what are the orientations on the boundary points? And again, what do you mean, orientation on a point? Well, it's an arbitrary attached, we're tacking on this notion, plus or minus, as an orientation on points. So here's the choice. It's arbitrary. This is the choice. The right endpoint is arbitrarily, but importantly, attached a positive orientation, and the left endpoint, arbitrarily but importantly, is attached with a negative orientation. So here we have an oriented domain, an interval, and it has now, because of these conventions, an oriented boundary. So the purpose of this discussion, again, is to talk about, what does this word mean, boundary, and you already knew, right, from way back when, that if you have an interval, then the boundary is a couple of points. What we're talking about now is if you have an orientation, then what's the boundary orientation? Right, so we're just talking about orientations right now. Okay, so we have to go and make an analogous collection of choices, conventions on, what do you mean by orientation on boundaries for all of our other kinds of domains. And here we go. Suppose you have a curve. I'm just going to draw a curve in 2 dimensions, but it's the same in 3 dimensions. Curves, again, have orientations. Pen. So there's a curve, oriented curve. And I want to know what is the oriented boundary of this curve. Well, here's the choice. And it's an arbitrary choice, but nevertheless, here it is. The end point. It's not about being the right or the left. It's about being the end point. Comes with a positive orientation. The starting point, don't care if it's on the right or the left, up or down, this way or that way. If it's where the curve starts, it gets a negative orientation. That's the convention. And by the way, you may notice that is kind of in line with this choice, with the understanding that, if we were to interpret a positive orientation on the interval as being kind of like it's oriented to the right, which, kind of feels right somehow, Anyway, with that interpretation, then it's a consistent choice. Okay, is everybody on board? Arbitrary choice, but still. Okay, now here's where it gets a little weirder. If we have a region, 2-dimensional region, okay, well now we have this notion of orientation on 2-dimensional regions. Right? Orientations on 2-dimensional regions. Again, it's just positive or negative. There's no geometric interpretation of what I would mean by a negatively oriented two-dimensional region. We're stapling this new concept of orientation, plus or minus, onto this existing idea of two-dimensional region. The boundary is a collection of curves, right? No big deal there. Of course they are. The boundary, you can see these curves right here. There's one of them. That's one of the curves. Here's another. This is part of the boundary. This is part of the boundary. Right? So, but again, the big question is about orientation. If I take this oriented yellow two-dimensional region, and let's say that it's positively oriented, just for as a starting to start the conversation, we're going to have a positively oriented two-dimensional region. What are the orientations on the boundary curve? Again, arbitrary choice. This is not something that you can drive for yourself or anything. It's a choice based on conventions that, again, were made a long time ago. And here's what the answer is. It's commonly misunderstood. A lot of people think that the choice is you go counterclockwise. It's not really quite exactly right. What it is that you always go along the curve in such a way that as you're moving along the curve, the region that you're part of the boundary of is on your left as you move in the correct direction along the boundary. And the emptiness, nothingness, is on your right. And if it's on the boundary, if we're talking about the boundary is, the line between set and not set. Right? So what you want to do, go in the direction that makes the region on your left, not region, emptiness, on your right. So you'll notice that means that on this outer, on this outer chunk of the boundary, it means we're going this way. Right? Notice that the region is on my left and emptiness is on my right. Okay? And a lot of people would say, see, look, it's counterclockwise, right? But here's the thing. Check it out. On this, on an interior piece of boundary, notice that's the direction you have to go to have the region on your left, emptiness on your right. And notice that this has you going clockwise, not counterclockwise. Okay, so heads up about this little, like I say, common oversimplification. Don't just assume it's always counterclockwise. But it's, if you're going around the outer piece, then yeah, the outer chunk of the boundary is counterclockwise. Okay. How are we doing? Does everybody understand what this convention is? Again, don't worry about why. There is no why. It's just a convention. It's a choice. We could have arbitrarily decided to go the other way. This is what planet Earth does, so we're going to go with this. Okay. All right. Moving along. What if you have a solid? Right. Well, solids are kind of hard to draw on paper. Now, I could have just drawn just a ball. Importantly, I'm not going to draw just a solid ball. I want to draw a hollow solid ball. You know what I mean? And so it's a three-dimensional solid, but it's a three-dimensional solid that's had a little cavern dug out from the middle of it. So let's talk about what's the boundary of this solid. Well, as a solid, if we're getting orientations as a solid alone, the boundary is pretty easy to talk about. The boundary is, this sphere. Now also, the boundary is got another chunk to it, and that's this sphere. Okay, so now let's talk about orientations. This solid, this yellow solid, and again, I'm going to, to start, assume that we have a positively oriented yellow solid there. Positively oriented, again, doesn't have a geometric meaning. It's an arbitrary notion that we're sort of tacking on to the existing idea of a solid. Positively oriented solid, boundary surface. What is the what we call induced orientation on the boundary. It's an arbitrary convention. Again, but don't look for reasons here. Here's the convention. The choice is commonly misunderstood. Again, there's a temptation to say that it's always outward. It's not quite true. The orientation on the boundary is always in the direction that is away from the solid and into the nothingness, into the empty, not solid. Right? Now, most of the time you're thinking, well, you got a solid away from the solid. Isn't that synonymous with outward? Well, not really. Let's look at that inner chunk. On that inner chunk there of the boundary, on that piece, solid is over here. Right? Emptiness is over there. So, away from the solid is actually not outward. If anything, you would have to call that inward. Okay, so again, don't think in terms of outward and inward. That's just not what the definition is, what the choice is about how orientations work. The orientation is away from the solid into the emptiness. Everybody on board? All right. Hope it's clear that this is, again, I already said this is for a positively oriented solid. Okay, so what if it were a negatively oriented solid? That's exactly what you would expect. It's just the negative of the otherwise orientation. So if this were a negatively oriented solid, then on the outer chunk, we'd be going into the solid. Exactly what you would expect. On the inner chunk, we've been going out instead of in. Okay. All right. Here's where the pictures start to get harder to draw. Let's talk now about a surface. Okay, so I'm gonna. You'll notice here I have drawn a surface. There's a surface, and the boundary of a surface, of course, is a curve. Then we recall, okay, yeah, sure, that's all well and good and that's simple, but we're not talking just about inert surfaces and their inert boundary curves. We're talking about oriented surfaces and oriented boundary curves. So the question is, if this is not just a inert surface, but an oriented surface. So I want to think of points at every point over here on the, every point over here on the surface there is, this unit normal vector. You might say this is a surface that's oriented upward. Given an orientation on the surface, which direction is the corresponding orientation on the boundary? Does the boundary orientation go that way or this way? Which is it? So again, the answer, it's a convention, it's just a choice, it's completely arbitrary. Well, it was completely arbitrary when the choice got made many years ago, but now we're going to get on board with what everyone else has already gotten on board with. So here's the convention. This is a little bit of a tough one to talk about. This is not a matter of, always outward, always inward. It's just not as, the lingo is not as convenient. So I'm going to have to go to a little bit of trouble to set up a technique that allows for discussing this. Here's the technique. There's different ways to say the following, something equivalent to the following. I'm going to show you the one I think is the most easy to understand and easy to deal with, easy to work with. Here it is. On your oriented surface, get a point that's close to the piece of boundary curve that you're interested in orienting. Just, nearby. Not on it. It's got to be close, but not on. With your right hand, flashbacks to chapter 1, right? So with your right hand, put your thumb in the direction of the surface's orientation. So by assumption, we're talking about an oriented surface. Thumb in the direction of the surface's orientation. And then look at your fingers. Right hand, very importantly, right hand. Look at the direction that your fingers want to curl around your thumb. Notice that that defines what I'm going to loosely call a swirl around that normal vector. Let's see here. I'll use, yeah, okay, so, whoops. I'll use this right here. Right, this is the direction, with my thumb pointing up, my fingers on my right hand want to go that way. It creates again, let's not worry about the rigor. There's a swirl going around that way, around that normal vector. Is everybody on board? That swirl side swipes up against the boundary curve in what I'm going to call the conventional, the correct direction for the orientation on the curve. And not hard to persuade yourself that that side swipe, in this case, as I have it drawn, normal vector up, swirl like this. This swirl side swipes up against the boundary curve. That way, not that way. So we now have a clear choice on what the orientation is on the boundary curve. Everybody on board? Yes.
Why do we use the left?
Yes, that's a great question. So that is an alternative formulation. So you may recall I mentioned that there's different ways to present the same idea. Let me run with that and let me show you. So this is here's a different way to think about the orientations here, and the alternative is to say always go around on the boundary such that the surface is on your left. Okay, but wait a minute. Who's left? Here's our little character that we're visualizing that's walking around the boundary, right? And there's tempting to say, well, on that person's left. What's the problem? Here's the problem. What about this person? Right? That person is also walking around this boundary curve. Is it on that person's left? And, yeah. Then you can kind of turn your head upside down and try to think about which way would the little green person have to walk so that the surface would be on his or her left. And it's pretty confusing, right? But I'm going to cut to the punchline, and you just have to think about it, right? The blue person walks that way to have the surface on his or her left. The little green person walks that way to make the surface, on his or her left. Right. So which person is it? Well, there's an answer to that question too. It's the person whose head is pointing in the direction of the normal vector that defines the orientation on the surface, right? So it's not that this can't be dealt with. It's that even though you can deal with it, it can get pretty confusing. Right? Does everybody see the problem? And actually, this segues very nicely into my next example. Let's think about orientations on this surface. So you can see I have a surface that's like a piece of paper that's kind of folded under itself, and then I've cut holes out of the sort of, if you will, the top and bottom pieces of this piece of paper. And well, the boundary consists of three curves. One of the boundary curves is that. Here, let me use a better color. One of the boundary curves is that. One of the boundary curves is that. And one of the boundary curves is that. So let's think through now. If the surface were oriented, here's my surface. I don't want to highlight the whole thing, but there's my surface. Suppose my surface is oriented this way, which by the way means like that, down on the bottom pieces, how are we going to decide what the orientation is? For example, let's say on this, let's look at this bottom piece of the curve, right? So you have two choices. You can try to imagine yourself being a little person walking upside down around this piece of curve. It's super confusing. I mean, you find yourself during the exam like, okay, so it's like that. And it's just hard, you know. But what is easy, relatively easy in all cases, is just turn your hand like this. Right? It is so much easier to see. Look over my right hand, thumb down, no problem. And look at my fingers. Look at my fingers are swirling, and that's just not a problem. So, not hard at all to persuade yourself that the finger swirl is like that. And how does that side swipe up against that piece of boundary curve? Well, that direction. Which gives you that orientation on that piece of boundary curve. Is everybody on board? Okay. All right. So it's a much harder problem. I mean, and I totally get where you're coming from. You know, your original question was motivated by, well, look, I mean, isn't it kind of morally not that different from this picture? Right? It's like, we got a two-dimensional thing with one-dimensional boundary curves. Let's just use the same convention we had here. But it is more complicated. Okay. Right. Okay, so those are the conventions. Let's take a quick summary of the objects and at least some of the conventions that we've just introduced. I'm going to organize these in 3 separate little diagrams. These diagrams are going to grow as we go through this material. Here's what I'm going to call our R1 diagram, our R2 diagram, and our R3 diagram. The way calculus works in these 3 different contexts, the calculus of R3, a little bit different from the calculus of R2. Which is a little different from the calculus of R1. The purpose of these diagrams is to take all these different ideas that we're going to be developing over time, over the next week or so, I guess, and keep them organized. Have a place for every idea that we develop. And what we're going to find and as we go through and develop these ideas is that if we're organized about where we think of which objects and which concepts is fitting in these diagrams, what we're going to find is that we notice a very strong pattern developing. It's unavoidably, obviously strong pattern. All right, so let's take a look at these diagrams real quick. We'll start with the R2 diagram, no particular reason here. And in this R2, actually I can zoom in one more, can't I? In this R2 diagram, we have 3 columns. You'll notice I'm going to call these columns 1, 2, and 3. This is to indicate the dimension of the corresponding domains. So points are 0-dimensional. Curves are 1-dimensional. Regions in R2 are 2-dimensional. Okay. These are the kinds of evaluations that, again, arbitrarily, and I know I pulled it out of a hat, I made some arbitrary choices, but we've decided that on curves, we're going to be interested in vector line integrals. Because I claim nice things are going to happen if we make this choice. Say on curves, the object in question is vector line integrals. This leads to good results. And likewise, double integrals. And, now there's an odd little sort of notion of a domain here of a single point, and what can you evaluate at a point? Well, a function. If you have a function and a point, you can plug the point into the function and out comes in a value. Okay. All right. So notice, functions are what you plug into points, like so. What do you pair with a curve to evaluate a vector line integral? Well, a vector field. What do you pair with a two-dimensional region to get a something you can evaluate as a double integral? Well, the function, this integrand, is a function. Okay, so these are the objects, these are the players on the field in R2. And notice we have a little bit of structure connecting these things. We've talked about boundaries. We've talked about what it means for the boundary of a region to be a curve. In fact, reminder, we've talked about what it means for the boundary of an oriented region to be an oriented curve. Arbitrary conventions. Likewise, boundary of an oriented curve is a pair of oriented points. Okay. Likewise, in 3 dimensions, it's a little bit more substantial because, well, in 3 dimensions we have an extra column. Recall, we made these choices. We're looking at triple integrals, fluxes, vector line integrals, and functions, the domains of which are, in columns 1 and 2, both vector fields. Right? And we have these choices about conventions on boundaries. We know what the orientation, the boundary of an oriented region is an oriented surface, et cetera, et cetera. Okay. So, a bunch of conventions. And then seemingly pointlessly, notice that there's still calculus in R1, and, we defined what we mean by the boundary of an oriented interval. We get oriented points, and we're talking about integrals in column 1, functions in column 0. I mean, this is seemingly kind of trivial. But this is going to be the starting point for our development. What we're going to do now is I'm going to play a certain game. There's a circumstance that I can consider here in R1. I'm going to think about how to play out a certain scenario, and we're going to notice a pattern of how the calculation goes. And quite surprisingly, that pattern is going to reproduce itself in R2 and in R3. Okay. All right, so here is the pattern I want to consider. Let's suppose that I have given to me some function in column 0. Now let's just say, it's my story, right? I'm making this up. So I'm going to start with, let's suppose, a function in column 0. And further, let's suppose that we have an interval in column 1. And what can I do here? How can I let this story kind of unfold? Well, I have an oriented interval. I have an existing operation that I can apply to that oriented interval. I can take the boundary of that oriented interval. Right? The boundary is going to be, let's see, do I have that down here? Here we go. Here's our function, column 0, an interval. In column 1, I can take the boundary. Here it is. The boundary is the endpoints A and B, oriented. Right? We have these arbitrary conventions that we made of, okay, the right endpoint gets a positive orientation, the left endpoint gets a negative orientation. Okay. Well, hey, now I've got, over in column 0, notice I have everything that I need to plug in to this evaluation. To plug into an evaluation, you need a function and you need points to plug into it. And then you can plug that into this formula for what we mean by evaluate. And out comes, and let me just, for notational convenience, just do that. What comes out is f of b minus f of a. And remember, there are these conventions for what we mean by plugging in, 2 points into a function. We mean just add the values. And what do we mean by a negative orientation on one of the points? A negative orientation means that when you plug that in, don't forget to put a minus sign on the output value. That was our arbitrary choice of what we mean by an orientation on a point. Okay, so again, we started with a function in column 0, an interval in column 1, and naturally this expression shows up, which is an eyebrow raiser, because we recognize this expression, right? This looks like it's kind of going somewhere. So the question that we want to ask is, can I view this as being something that got evaluated in column 1? Can I view this somehow as being an integral? Notice if I wanted this to be an integral, I would need to have something there. I would need an integrand in column 1. So let me rephrase the question. Is there something that I can do to my original function? Can I take that function and do a certain, let me be vague. Is there some process, operator, or something I can do to give me something so that that evaluation will give me the same result? Now, y'all know the answer to this question, right? I mean, the question has become, is f of b minus f of a the integral of something? And of course it is. It's derivative, right? I mean, we all remember the fundamental theorem of calculus, right? But I wanted to point this out as a question, and the argument that I'm going to make is that really what we're trying to do is we're trying to motivate an operator there that's kind of sort of complementary to the boundary operator, right? So in the same sense that the boundary operator gives me the opportunity to do an evaluation, I'd like to know, is there a different operator on integrands that allows me to evaluate and get the same result? So these kind of complementary, I think, is a reasonable choice of word there. Okay. So that's the question. Now, notice I'm trying to get this to look like an integral. An integral is a summation. I would like to figure out then, can I view f of b minus f of a as a summation? Specifically, it needs to be a summation that's happening over an interval, this interval from a to b. Does this expression somehow add up over the interval? And yeah, well, of course it does. This is another thing that I know y'all have seen before. So let me go back up to this diagram. I know y'all have seen this a million times, right? But if you take your interval from a to b, and if you chop it up into sub-intervals, right? Different ways to write this. Let me write it in a sort of a new way. But if I look at I1, and specifically its boundary is going to consist of these 2 points, this one with a negative orientation, this one with a positive orientation. Now let's talk about I2. Let's look at the boundary of I2. The boundary of I2 is going to consist of these 2 points, this one with a negative orientation, this one with a positive orientation, etc., etc., etc. Check it out, though. As I continue along, notice that this x1, the x1 is part of the boundary of I1, the positive orientation, but it's also part of the boundary of I2, but with a negative orientation. So when I start adding up these boundaries, the boundary of I1 plus the boundary of I2, etc., I get x1 appears twice with opposite signs, and they cancel. It just disappears, right? So, in fact, that's going to disappear due to canceling signs as parts of the boundary of I1 and I2 respectively. X2 is going to disappear due to canceling signs as parts of the boundaries of I2 and I3, etc., etc. All of these midpoints, all of these interior subinterval endpoints, I'll cancel them. All right, now you can see the algebra of that laid out. If you add up the boundaries of all those little pieces, let's stretch that out. There's the boundary of I1. Here's the boundary of I2, et cetera, et cetera, et cetera. And just as we observed on the previous page, here is how x1 appears twice, right? x1 is positive oriented as part of the boundary of I1, negative oriented as part of the boundary of I2. Same thing, opposite signs. Cancellation. Likewise, all the other interior points, you can just see these cancellations continuing, right, all the way over to, here's xn minus 1. That appears twice, but with opposite signs, and those, therefore, cancel. And notice all that is left is a negatively oriented x0, otherwise known as A, and a positively oriented xn, otherwise known as B. Namely, I get exactly the boundary of the entire interval. All right, so I hope that this maybe not the exact presentation, but this kind of you all heard this described as a telescoping sum, I think, right? So this sort of algebraic phenomenon you've seen before. Here's another way to write it. I wrote it from the sort of the point of view of domains and boundaries and orientations there. But the algebra, if you just take f of this entire thing, just apply the function, and keep in mind, the arithmetic on domains just means what happens in the arithmetic after you evaluate things. Right? The arithmetic's the same. The way you may have seen this in a Calc 1 class is that f of b minus f of a is what you get when you take all of these pieces and add them up, because there's cancellations. That cancels with the next term. There's more cancellation in the middle. Oh, I didn't leave myself enough room here, did I? But that cancels with something else, and you're left with just f of x1. Oops, I canceled the wrong one. Colors, sorry. This cancels with that. I'm sorry, that's got ahead of myself. It's the x1 that cancels, etc. And then lastly, the xn minus 1 that cancels. And you're left with minus f of x0 and plus f of xn. So maybe you've seen it written like this instead. Same sort of cancellation. Okay. All right. All of this is just to go to motivate this first line here, which is f of b minus f of a, the object that we're interested in. I can view that as just a summation of similar looking expressions defined on the subintervals. All right. So look at this formula here if you like. F of b minus f of a is a summation passing over the subintervals. Now let me take a pause. Let's go back over here. Reminder, that's what I was kind of aiming for, right? We took the boundary of our interval. We plugged into the evaluation. We got f of b minus f of a, and we decided we wanted to try to view, can I view f of b minus f of a as being something that is a summation over the interval. And we've got that now. Right? F of b minus f of a is a summation over the interval. Everybody with me? Okay. Now our eventual goal is to actually rewrite that as an actual integral. I want it to be integral from A to B of something, so that I can figure out, exactly what is this integrand, because that, whatever that ends up being, that's going to tell me what this operator is that I'm trying to motivate. All right. So I've got to take this summation, and I've got to turn this into an actual integral. And this is actually no big deal. Some of y'all may have seen this algebra or something like it in a Calc 1, Calc 2 class. So this summation is True for all values of n. So I can say limit as n approaches infinity. It doesn't cost me anything to let n approach it. If this is constant, this is always the same thing. Who cares what n's doing? I'm going to multiply and divide by delta x. That's perfectly legal. Didn't do anything there. Right? So I still haven't really done anything. Notice now what I have on the inside could be rewritten as delta f over delta x. After all, this numerator is the change in the value of the function. So delta f, a reasonable choice. And now this is looking an awful lot like a Riemann sum. Namely, it looks an awful lot like an integral. So I am going to have to sweep a little bit of difficulty under the rug. This is something that, as engineers, you don't need to worry about. If those of you who might become math majors, when you take a real analysis course, then this will be treated much more carefully than what I'm about to do here. But I think it's plausible and perfectly appropriate in this context that, look, we're taking a limit here, and so even though delta f over delta x is the actual integrand, I need to rewrite that as, I need for this limit, you might say, to pop inside of the summation. And there's a kind of a sticky wicket there. This is not something that's perfectly obvious that you can do. But that's a matter for an analysis class. In a class like this, I'm just going to assert what I think is quite plausible, that for appropriately regular functions, as long as nothing weird's happening, pretty believable, I think. Okay. Anyway, having swept that under the rug, notice that now we have what's an integral, and furthermore, this integrand is familiar. That is exactly the definition of f prime. And look what we got. We have our fundamental theorem of calculus. More to the point, we have what we stated as our goal. We've managed to find a way to view f of b minus f of a as an integral of something. That something is f prime. So I'm going to go back up here to my, where we were. I had f of b minus f of a. My goal was to view it as an integral of something, and so that I could identify what that something is so that I could know what operator to put there. And now I see that that something is the derivative. So I'm going to put the derivative, up there as an operator. Notice our diagram just got a little bit bigger. Previous to now, our diagram was just, we had boundary, that's it. Now, I have boundary as an arrow going to the left in the domains, and I have a new arrow that says if you have a function in column 0, the derivative is the thing that gives you an integrand in column 1. So, in fact, here it is. Here is our appended diagram. It's just grown by the inclusion of that derivative operator. And here then is, this is the weirdest way you've ever seen the fundamental theorem of calculus written, I'll bet. But the fundamental theorem of calculus is, I'm stating here as that this evaluation and this evaluation give you the same value. Okay, how we doing? Now, I know y'all knew this result already, of course. My goal here was not to make sure that y'all saw a certain kind of a point of view on the fundamental theorem of calculus. That's not that much. As I often do in this class, the purpose of this little exercise was to set up a pattern and then apply that pattern in the multivariable context. And the purpose of this little exercise was as a segue, right? So that I can do this in a multivariable context. And what I mean by this is we're going to take this little diagram chase that this little game where we go over there, push down, see if you can get this over here, make a new arrow, and this whole thing. We're going to try to follow that exact pattern in the other diagrams with our fingers crossed, and hopefully something good will happen. And of course, I'm not going to waste your time. Of course, something will happen, right? Okay. Quick pause, though. Does anybody have any questions about what we've just done? Okay. All right. Again, the pattern is the most important thing here. Okay, so let's try to apply this in 2 dimensions. Now, there's a couple of different places where I could reasonably ask if the pattern continues. So I could look between column 0 and column 1 and say, hey, if I do that and push down and, what happens over here? That's one thing I could ask. Or I could maybe ask over here, hey, what would happen if I took a boundary of a region and pushed down? And what would I get? Can I rewrite it over here, etc.? We're going to start with this over here, but we will later, FYI, we will be doing this pretty soon, and the pattern's going to be the same. The geometry is going to be totally different, but the pattern is going to be the same. That's just a little foreshadowing. Let's get down to business with this. We're going to assume we have a integrand in column 0, a domain in column 1. Notice our domain in column 1 now, it's not an interval, because we're not in R1 anymore. We're in R2. Column 1 domains in R2 are curves, oriented curves. Okay, so we are going to, again, following the pattern, just with fingers crossed, hoping that, hey, if I do the same little dance over here in this other part of the floor, does it work out? Let's just try it. Blind faith. Hopeful. Let's talk about the boundary of that curve. Let's plug that boundary into the function that we were given, and let's see what happens. And of course, no surprise. I mean, you get f of b minus f of a, and the question we want to ask is, can I view f of b minus f of a as being a summation over the curve? So that's what we're going to come back up here to and ask: is f of b minus f of a summation over this curve? And I'm going to do this from the picture for sort of convenience. Here's our curve, oriented curve, that is. I'm going to chop this thing up into little pieces. And proceed as we did previously. So I'm going to call A x0, and then I'm going to call this point here x1, and that point x2, etc., etc., etc. Notice on this piece here, on my ith piece of curve, I have xi minus 1 as the starting endpoint, and the xi is my ending endpoint. And notice that, let's see, I think I have this written down. Yeah, here it is. The boundary of the entire curve, well, the boundary of the entire curve is positively oriented B, negatively oriented A. Right? It is a summation of the little interior boundaries. Looking one at a time, the boundary of C1, let's come up here. The boundary of C1, boundary of that little piece of curve right there, it's the points x0 and x1, but oriented a certain way, right? Negatively oriented x0, positively oriented x1. And so I get this. The next piece, its boundary is negatively oriented x1, positively oriented x2. And just as we saw before, x1 appears twice, First as part of the boundary of one of the pieces, then as part of the boundary of the other pieces, but it appears twice, but with opposite orientations, and they cancel. And likewise, everything else in the interior cancels. And again, you're left with just a negatively oriented starting point and a positively oriented ending point. By the way, you'll even notice the layout on the page. I did this on purpose. The layout on the page of that algebra is exactly the same as the layout on the page of this algebra concerning intervals. It's the same. I mean, really, really similar. In fact, I think when I did when I wrote this part of the book, I think what I did is I did a copy paste here, and then I just put little vector symbols over every little x. Pretty much everything's the same. Okay. So same kind of cancellation. We end up with here's the same thing, just in the language of evaluated functions. F of b minus f of a is what you get when you add up similar looking expressions defined on the individual intervals. And as desired, f of b minus f of a is, you can see it right here, it is a summation happening over the curve. This is a summation happening over the curve because each one of these is computed on the little piece of curve. Okay. All right. Okay, so how do I actually write that, however, as an actual integral? Specifically, it acts as an actual vector line integral. How does that happen? Okay, well, and by the way, what on earth is that vector field? Nobody said anything about a vector field yet, right? All we've got is a function here. What vector field? Right? So one of our big goals is to figure out, well, there's going to be a vector field over here. How does that vector field come about? Namely, what is that arrow? So that's what we're going to try to develop. Okay. So it's just a little bit of algebra at this point. So here we have our above observation about how f of b minus f of a is a summation. Notice that the summand here I could reasonably call delta f. Right? After all, each one of these little expressions says how much does f change between two nearby points. So I'm going to call it delta f. Further notice, I can let n approach infinity. It doesn't matter. All of these things add up to the exact same thing. This is just a bunch of different summations that all equal a constant f of b minus f of a. So the limit is, taking a limit of a constant doesn't matter. Okay. And now I remind you, chapter 4 callback. Output changes relate to input changes. Right? The relationship between how much f changed between these two x values relates to the change in the x values itself. Input change, output change are related by the derivative transformation, the Jacobian matrix, however you want to say it. We're assuming this function's appropriately differentiable. Gradient vector. In this case, we're looking at a real value function. So, dot product with the gradient vector relates the input change delta x with the output change delta f. Okay. And looky what we've got here. That is exactly a vector line integral. I've got a limit of sum of a vector field dot delta x. And flip on back to section 5 point whatever where we define vector line integral. That is exactly the structure of a vector line integral. Specifically, this is a vector line integral of the gradient of f. Everybody on board? Sweet. So that was my goal. Look, my goal was to figure out how to rewrite f of b minus f of a as a vector line integral of some vector field. Coming back to, again, where we were in our diagram. In fact, here we go. So I took the boundary, evaluated. We're looking at f of b minus f of a. We wanted to figure out how can I write that as a vector line integral. And specifically, what is this vector field? Right? What is that operator? What do I do to little f in order to make a vector field such that gives me the same thing, right? And we have an answer to that question now. The answer is gradient, right? This thing right here, that is the gradient operator. Okay, so this is our little summary of what happened. Again, we took a boundary, we plugged into a function, we got this expression, and we have now seen that if you take the gradient of the original function and do that evaluation, namely, take your new gradient vector field, your original curve as a domain, do the agreed upon, arbitrarily chosen, but agreed upon vector line integral of that vector field over that curve, then you get a value which is always the same as the blue calculation. Said differently, these operators are kind of complementary in this context. So this is really very much, we just ripped off, it was a borderline shameless rip-off of the fundamental theorem of calculus. We're just going to take this little strategy, we're going to kind of apply it in a slightly different setting, and it's almost dishonest for us to claim credit for coming up with a new result here. It's kind of the exact same thing as fundamental theorem of calculus. Nevertheless, it is in a pretty different context. Right, we're in R2 now. We're moving around some curve in space. The gradient is, it's kind of like the derivative in a Calc 1 context, but it is in a very different context, and this is a pretty different result. So it is a different theorem. Nevertheless, we are going to motivate this, the name for this, with that connection. This is called the fundamental theorem of line integrals. Where did I write this down? Here it is. Fundamental theorem of line integrals in R2. Because it's kind of like the fundamental theorem of calculus. Everybody on board? By the way, here's a little cultural note. This little practice that we just committed of let's take a known established theorem, fundamental theorem of calculus. Let's look at it in a certain way, kind of notice a way of thinking about it, and then let's take that way of thinking about it and apply it in a different setting, and let's see if we get a new result, which paid off very nicely here. That strategy of taking, trying to strip away the peculiarities and the arbitrary, the specifics of context, strip away and get the fundamental core idea out of something and use that core idea in other places. That's one of the big ideas in math. That's how a lot of math gets done. It is a very important concept to kind of be aware of. Lots of math comes about by taking ideas that worked well in one context and, hey, well, let's see if it works over here too. Okay. So, okay. So, very good. Here's our now appended diagram. Remember, we started off with just that one arrow. We had these things here, but we didn't have previously anything here, but now we do. Gradient, new object on our diagram, and having appended our diagram like so, we have here's how I'm going to represent the fundamental theorem of line integrals, just from a pattern point of view. Boundary and gradient are complementary in the sense that these two evaluations give the same thing. Alrighty. Okay, so I hope it's no surprise, and I'm going to do an example in just a moment, that in 3 dimensions, very, very analogous argument holds. This would be a good exercise for y'all to think about on your own, by the way. I mean, how can you do this? The same analysis that we just did in 2 dimensions, same thing in 3 dimensions. And just think it through. And I'm going to give you a huge hint as to how that argument goes. You're going to use this picture, right? You're going to break it up in the same way. You're just going to change it a little bit. Now it's a picture in 3 dimensions. Right? And change the axes appropriately, I guess. But if the curve is in 3 dimensions, you can still break it up into pieces. On each piece, the boundary is still these 2 points, negative and positive, appropriately. And then the next one, 2 points, negative and positive, appropriately. This one's still going to appear twice, once with a negative, once with a positive. Everything's going to go through exactly the same. It's really exactly the same. It's just that now there's 3 dimensions in our picture. These vectors are now points in R3 instead of points in R2, but I'm still representing it as vectors. Okay? So the argument is really, really, really very much the same. So I'm not going to write it down, but again, it is a nice little exercise to think it through. We do get the same result, the fundamental theorem of line integrals in R3. Same story as in R2. We're going to append the diagram analogously by adding gradient arrow in our R3 diagram. Our brand new fundamental theorem of line integrals in R3. Again, I can write it as boundary and gradient lead to evaluations that always give you the same result. Everything's the same. Okay, so let's get our hands dirty. Let's see an actual example. Now, how can we actually use this? I'm going to start with this example here. We want to compute a line integral, and we've got a vector field given, and we've got a curve given. In fact, not only is the curve given, but the curve is parameterized. Now, there is a strong temptation. Those of you who have done the exercises for, the vector line integrals section in chapter 5, I hope it's all to say, okay, well, look, we've got a parameterization, and the way you compute a line integral of a vector field is you take your parameterization and you've got to compute x prime. You take that's your v, and then this is integral of f dot x prime dt, and take a deep breath, and then plow through all those details, right? And of course, in the process of doing so, don't forget that this is your x, which of course you have to plug into your vector field, and this is your y, and likewise this is your z, right? So this vector field is going to turn into a pretty ugly customer. X prime is going to be a pretty ugly customer. You're going to have, when you actually write down that dot product, f dot x prime, it's going to be a monster. It's going to be kind of obscene, right? Horrifying mass of algebraic inconvenience. So you could do that, I suppose. Well, let's call that plan B. Can we think of a better way to do this? Hopefully it comes as no surprise. We're going to use this theorem right here that we just came up with. Notice that this theorem says you can compute a line integral with a formula. How's that for nice, right? Hey, sweet, can we use it? Wait a second. Now, this isn't just any random line integral. We're interested in computing a line integral of this thing called f. The theorem allows us only to compute line integrals of gradients. I have got to decide now, is this vector field, it's not obvious, is that vector field a gradient? Notice, this theorem does not say anything about line integrals of vector fields that aren't gradients. Right? It's specifically line integral of gradient only. Oh, okay, so, there's a technique for deciding this, deciding if a vector field is or is not a gradient. We'll get to that after the break. Here, I'm just to kind of get our hands, successfully dirty and just see the mechanics of how the theorem works. I'm going to go ahead and just point out that, hey, check it out. This function here, that function, its gradient is the f that we are interested in, and so yes, we are looking at a line integral of a gradient. We're looking at a line integral of the gradient of that function. Now, where I got this function from, for the moment, it's a magic trick, right? Well, I'll pull the curtain back after the break, but just for mechanics purposes, again, notice take this function, write down its gradient, you get this. So therefore, we are taking a line integral of a gradient. Okay, and so having observed that, this function, which by the way, I hope this seems plausible. I like to call that the anti-gradient. Right? When you undo the derivative, we call it the antiderivative. Here we're kind of undoing the gradient. I think anti-gradient, reasonable choice. That's the function that you use in this f of b minus f of a, and it's just really a matter of plugging in. Here we are. There's f that we're going to use f of b minus f of a. Notice our starting point is what happens when you plug in 0 into the parameterization. Our ending point is what you get when you plug 1 into the parameterization. That's just plugging in. Right? Starting ending values of d. T give you starting and ending values of x. Namely, gives you the a and the b that you plug into the f and arithmetic. And our answer is that the integral is 1. Right? So the monstrous calculation that would have been, we just bypassed it by making a clever observation. Oh, hey, check it out. We're looking at a gradient. There's the anti-gradient. We cite this very powerful theorem that says horrifying calculation alternatively can be computed with this simple formula. Everybody happy? Okay. There's a lot more to say. We will say it after we take a break. See y'all in a few. 10 minutes. So why don't we say, how about we say 11:20?